same example. Let's now look into part B of our current example. So again, this part B of our example still draw a common information that pulse rates generally have a known standard deviation of 4 BPM. But now, specifically in part B, we're looking at a sample of 74 people gives a mean pulse rate of 73.65 BPM, beats per minute. It looks like we're also using the same sample from the previous question, previous part of the example. But then at significance level 0.001 is the sample of pulse rates, showing strong evidence that generally mean pulse rate should be less than 80 beats per minute. So now here in our first responsibility, we must be able to identify the two hypotheses. So H0 for the null hypothesis and H1 for the alternative hypothesis. Again, into the actual question right here. This time we're looking at is a sample of pulse rate showing strong evidence that generally mean pulse rate should be less than 80 beats per minute. And mean pulse rate is once again is a population mean value. And we would like in this problem we would like to prove that mean pulse rate is generally less than 80 beats per minute. And so in that way, the statement itself right out from the wording, and now translated into symbolic statements right here, we already had an inequality statement. So being an inequality statement, this is perfect for nailing down our alternative hypothesis to be mu less than 80. And so in that way, the null hypothesis will come out simply just being mu equals 80. And just like how I have explained earlier, and just like how we have seen back in the general discussion, the general understanding of testing a hypothesis, then going from alternative hypothesis to the null hypothesis, all we do here is simply to replace the inequality with the equal sign. Unlike the earlier problem in part A, this alternative hypothesis this time is having a statement where the inequality is pointing to the left. So in that way, I am introducing another term. That's this test we are about to run, this test we are about to proceed is being regarded as the left tail test. And again, allow me to wait until the end of the problem where I have successfully put in all the steps together. Then I will explain what it means by being a left tail test. Now, first step into the actual problem for testing our hypothesis. Once again, we must identify our sample and clearly indicate that. So our sample here in this case is we're testing a value about a population mean value. So the sample we're using here is of course a sample mean value. Back in the question itself, a sample of 74 people gives a mean pulse rate of 73.65 beats per minute. So the information that I just now highlighted is now a given sample mean information for us. So we have a sample mean being 73.65, which happens to be the same sample we used in the previous part of the example. This sample came out from a sample size of 74. So there are 74 pulse rates in our sample. And so after identifying our sample mean that we use as evidence in the first step, the next step now is to realize that once we have a sample mean value, then this is not the only sample mean value ever exists out there. There are infinitely many other sample mean values existing out there. And so in that way, really the next step now is to find the center or the average of all sample means. So symbolically, it's mu x bar. This average, this center of all sample mean values will be equal to 80. And allow me to wait until after we finish putting all the steps together to give out the actual explanation of why and how I came up with mu x bar equal to 80 here. But what we can notice at this point is that mu x bar, or the center of all sample values, must always be the same as the value being claimed in our null hypothesis. And in the next step, as a little step, but quite important as well, we must again realize that since our sample value we're using here, being a sample mean value, is not the only sample mean existing out there, and there are infinitely many of those. So in that way, there is an average spreading, or a standard deviation. That's how we can formally call that. A standard deviation of all sample mean values. And symbolically, we notate that by a sigma x bar. One more time back to the computer screen. Even though we're now in part B of the example 1, but in the end, part B of example 1 still draws some common information carried over from the previous example, from the previous problem. Pulse rates generally have a known standard deviation of 4 BPM, which means what we have here is already a known sigma. So that known sigma of our is 4. And now we're going to divide according to the central limit theorem. We are going to divide by the square root of 74. So now final calculation for this sigma x bar comes out to be 0.46. And as I said in the earlier part of this video, then many different applications have different requirements for how far to round the sigma x bar value in terms of how many decimal places. So make sure when you're doing your real problem, watch out for those different requirements of how far to round sigma x bar. But here, for the rest of the video lecture here, I am mostly going to stay with 2 decimal places for our sigma x bar values. So here sigma x bar equals 4 divided by square root 74, and in decimal 0.46. That is the average spread of all sample mean values around this center. And then in the next step, again, since our sample mean is not the only sample mean existing out there, there are infinitely many. So at least what we know is right from where our sample mean is relative to the center of all sample mean values, then we have a z-score for our particular sample mean. Symbolically, z-score, but I use an optional subscript x bar here to indicate this is the z-score specifically for our sample mean that we are currently having. And then calculating z-score is just like how it has always been. The value of our sample is 73.65. Subtract the center of all sample mean values and divide by 0.46. This 0.46, note how it came from the sigma x bar value. Final calculation comes out to be negative 13.8. And as I have said in other videos, and including the earlier part of this video, unless being specified otherwise, usually for any z-score, I'm going with 2 decimal places. And in our case here, the calculation forces down to only 1 decimal here. But so this says the z-score for our particular sample mean that we're using here is a negative z-score, negative 13.8. Let's quickly pause for a consistency checkpoint here. So at this point, we have found our z-score, the z-score of our sample. This z-score of our sample is consistent with the alternative hypothesis in the way that it's a negative z-score, and our hypothesis is stating that the mean value should be, the general mean pulse rate should be generally below 80, or being to the left side inequality. Further, this z-score is consistent with what we have decided earlier, that our test was going to be a left-tail test. So left-tail test is consistent with our z-score being a negative z-score. And now for the next step. After getting the z-score for our sample, we are going to set up a probability calculation. I'm going to say among all sample mean values of size 74. I am looking for the probability where we run into a sample mean. This time, being a left-tail test, I am going to be setting up a probability. I'm looking for sample mean falling below, less than or equal 73.65. And so another checkpoint for consistency here. But this inequality here, symbolically pointing to the left, is to be consistent with the fact that our test was decided previously to be a left-tail test. And the alternative hypothesis was saying less than 80. So here we're using less than or equal to. The value that we're setting up in our symbolic statement of our probability problem should be always our sample value that we are using. And once again, allow me to give all that explanation of how I set it up and why I'm setting it up this way at the end of the problem, where I have successfully put all the steps together and come all the way to our final conclusion. But so this probability value, once we've found the value, we're going to regard to that as the p-value of our sample. So now, getting into calculating this p-value or calculating this probability, imagine that now you're on a bell curve where this line is where we put our sample mean values of size 74. So capital X bar 74 is found anywhere here. Then being a 73.65 is somewhere on the bell curve, and we're looking for how much area being shaded to the left-hand side. And once again, that's how it's called a left-tail test. And I will get to the actual real good detail explaining the connection between the left-tail test and this left shaded area when we're done with after we put all the steps together. But now, since we already had z-score for our sample, this probability problem is the same, or this shaded area on this bell curve here is the same as the probability that on the standard normal distribution, we're having z-score less than or equal to negative 13.8. And so now, proceeding further to find this probability on the standard normal distribution curve, it is now just a matter of running our LS&D program that we have used so many times throughout our learning, our course here. And when the program is asking for a z-score, we are going to provide negative 13.8. And since the area shaded in the picture here is to the left, there is no need to subtract the answer from 1. And now, with my INVZ program currently running on the computer screen, let's now enter negative 13.8 into the box that's asking for z-score, and the result here means 1.274 times 10 to the negative 43rd power. And so our final p-value calculation comes out to be, in 4 decimals, 0.000. And again, unless being specified otherwise, usually my final p-value is being rounded to 4 decimal places. So now that we have arrived at our final p-value, but how do we go from here to decide whether we have had our sample being a strong evidence or not? The key to our decision is here. So back to the question itself, we had a given significance level being 0.001. 0.001. So to decide whether our sample pose rate is a strong evidence or not, we can just simply compare this p-value with the significance level. And in this case, our p-value falls well below the significance level. That is enough for us to lead to this final conclusion that our sample is strong evidence. And strong evidence for what purpose? We have strong evidence, our sample is strong evidence for us to reject H sub 0, the null hypothesis. The statement whoever made that to claim that mean pose rate generally is equal to 80. Now we must reject that since our evidence here is strong evidence. Or we can say our sample is strong evidence to support the alternative hypothesis, H1. That's another way of saying that the alternative hypothesis says generally mean pose rate should be less than 80 beats per minute. And now altogether, in the end, this question itself is ultimately a yes or no question. Look exactly at the way how it's written. Is the sample of pose rate showing strong evidence? So the question itself ultimately is looking for whether or not we're having strong evidence. And we just now concluded that we do have strong evidence. Our sample is strong evidence. So the answer to the ultimate question now is yes. Yes, we have strong evidence. Our sample is showing strong evidence. All right, so now let's look at the explanations for each of the steps that was done in the example 1, part B. So allow me to pick up from after we have already found our two hypotheses. But briefly, let me remind what the two hypotheses were. So our null hypothesis was stating that mu equals 80. And the alternative hypothesis was stating that mu is suggested to be less than 80. And think of H1 here as a counter argument of H sub 0. And again, before I proceed any further into the testing hypothesis, then keep in mind again, after so many explanations of mine, that this value being stated in our null hypothesis is being regarded as a claim value. So in other words, H sub 0 is bringing up a claim stating that mu, the population mean value for pose rate beating, is at 80 beats per minute or 80 BPM. And so that is a claim value. And anyone viewing the video at this point has seen the step where I was indicating that this problem was a left tail test. However, among the explanation right now, let me hold on to the explanation of why this is a left tail test. And for now, let's not be worried about what this test is in terms of being a left tail or a right tail. We will get to that as soon as we finish with a few explanations here. But now we've learned from the steps that we already had a sample, and our sample that we used here as a sample mean value was 73.65. And this sample was at sample size being 74. And so now what we need to realize here is that, and this idea has been brought up so many times throughout other testing hypothesis problems, and we have studied this in the earlier part of the quarter, that once we can pick up a sample, provided that we're in this given sample size right here. So again, I repeat, once we can pick up a sample, then we must realize that this is not the only sample mean value that we can get. Indeed, there are infinitely many other sample means out there at the same sample size given here. And so in that way, I'm defining a random variable capital X bar with a subscript 74 here. This random variable is to represent the mean pulse rate but only in a sample of 74 people. And briefly recall from the idea that back in the days we were learning about the central limit theorem as well as the sampling distribution of a mean. Then this subscript I use here optionally is to indicate that each sample mean value being assigned to this variable is a sample mean that came out from a sample size, from a sample at size 74. And so once again, and this is a population of sample mean values, just to re-emphasize that idea again. And so now, since we understand that we're not only having one sample mean, but our sample mean is indeed one among infinitely many other sample means out there, then we have learned that this distribution of all sample mean values has an average, because in the end this distribution of sample mean values is a population of sample mean values. And so this mu x bar is the average of all sample mean values. And we've learned from the central limit theorem that mu x bar must equal mu. And further, since again this is a population of sample mean values and there are infinitely many sample mean values being represented by this random variable, our sample mean value is only one among infinitely many. And so it makes sense that there is a population standard deviation of all sample mean values. And we have already learned again that central limit theorem guaranteed that this value sigma x bar must equal sigma divided by square root of n. Sigma here is the population standard deviation from the beginning population, the population where we picked our sample from. And this is the sample size that each of our samples is currently being in. So these are a brief reminder about the central limit theorem and how it will be applied here. And so now once we recall the idea about central limit theorem, as well as we realize that our sample is only one value among the population of all sample mean values out there at this sample size, then here's the logic that we will start out. So in the end, again, keep in mind that we still do not know what the truthful population mean value of pulse rate out there is. But in this case right here, since we already had a claim, so I am going to start out by saying what if h sub 0 was true? Or in other words, what if we accepted this claim to be the truthful population mean value? As a reminder, h of 0 was true means we're accepting that mu, the mean pulse rate, the population mean pulse rate, truly equals 80. So what if we accepted that? So now, if we accepted h sub 0 to be true, then immediately, according to the central limit theorem that guarantees mu x bar equals mu right here, then we're going to consequently have, according to what's stated in the central limit theorem, mu x bar in this case would consequently equal to 80. And so now I have this value being equal to mu x bar simply because, again, central limit theorem is stating that mu x bar must always equal mu. And in this case right here, we are currently accepting that mu equals 80. And that's how I can lead to saying that mu x bar must equal 80 as a consequence. And so as a further consequence, the average spreading or standard deviation of all sample mean values out there can be found by, according to central limit theorem, sigma over square root of n, as you recall. But sigma, now once again, let's look back at the wording of our problem. In the wording of our problem, we had a known standard deviation. So again, I have emphasized in earlier part of the example, and now I can quickly emphasize again, but this description here, pulse rates generally have a known standard deviation of 4 beats per minute. This description is independent with any sample that's being selected out from that population. Or in other words, any description here of any sample has nothing to do or will not change the value of the standard deviation here. So this value that I'm about to highlight right here is the value of our sigma. So now I can take sigma here to be 4. And now clearly we're going to divide by square root of 74. And so calculation of mine came out to be 0.46. And indeed, this calculation here at first came out a lot longer, but unless being specified otherwise, then usually in any of my examples or in any of my lecture, then I am going to be using 2 decimal places for sigma x bar values. And so now, at this point, once we have had our sigma x bar value, then we must understand that this mu x bar is being understood as the center of all sample mean values at this sample size. And this standard deviation of sample mean values is, as its meaning, the average of all spreading. Or in other words, for short, we call it's the average spread of all sample mean values, how sample mean values are being spread away from the center. And so in that way, since we now realized already that our sample mean value being 73.65 is not the only sample. It is indeed only one sample mean values among infinitely many other sample mean values out there. And so from where this particular sample mean value that we have, from where it stands right here relative to this center being 80, then consequently I'm going to do this math right here, 73.65 minus 80. This is the center of all sample mean values. And I'm going to divide by the standard deviation of all sample mean values, 0.46 in the denominator. This work right here is the calculation of my z-score, but this is the z-score for my sample mean value. Calculation now came out to be negative 13.8. And again, the actual calculation came out a lot longer than this, but unless being specified otherwise, usually for z-score, I am going with only 2 decimal places. And in this situation, if anyone doing the actual calculation independent from with my video lesson here, then you can see that rounding down to 2 decimal places, in this case, particular case, forces us down to only 1 decimal here. And again, like the previous part of this current example, I am using a subscript x bar right here to indicate that this is a z-score, a special z-score. Just like any other z-score, this is the way how we're finding it, but this z-score is a special z-score because it's the z-score reflecting our sample mean value, how far it stands away from the center. So that is the z-score we have had for our current sample mean value. And so now, back in the wording description of our problem, then the only description about our beginning population is here. Pulse rates generally have a known standard deviation. So having a sigma value is the only thing we know. But as far as distribution shape for this beginning population, we have no information or no clue. Back on my writing board right here. But now since our sample size currently used is well above 30, this makes our sampling distribution of all sample mean values qualified to be on a bell curve. And this observation came out from the statement that was stated in the central limit theorem, a conclusion that was stated in the central limit theorem, that as long as our sample size is being above 30, then the sampling distribution of the mean values is going to be on a bell curve. And that bell curve now would have the following characteristics. It's going to have center at 80, and with the average spread being 0.46. And now we can imagine that we have a bell curve, a nice bell curve with a center at 80. And so on this line right here, anywhere left and right of this center, so this center came out from our claim value in the null hypothesis, but now left and right are different random sample values, sample mean values at size 74. And so that's why I can now label capital X bar 74 is to be arranged on this horizontal line right here. And this is the reason why now among the steps that we have seen earlier, and then when it came down to calculating, when it came down to that step, calculating the p-value, then we were able to, and by the way, the p-value was, as a calculation setup, the p-value was calculated as the probability that among all sample mean values here, we are looking for our sample mean at size 74 to be less than or equal to 73.65. And so now back to what I was saying earlier. When it came down to this step right here, calculating the p-value, then we were able to fire up this calculation as a bell curve problem, because we have just now proven that our sampling distribution of the means is on a bell curve. And so once we realize that our sample mean is on a bell curve, then this p-value calculation, this probability is the same as the probability that on the standard normal distribution bell curve we're looking for a z-score as being less than or equal to negative 13.8. This calculation of the p-value was made possible simply because we have successfully proven that our sampling distribution of the means, of the sample means, is on a bell curve. This probability is graphically understood as, think about from where our sample value stands. Obviously, 73.65 is somewhere on the left-hand side of this claim in the center. But this calculation is graphically represented as an area shaded to the left-hand side of the sample mean value that we are doing. And then getting to the actual calculation of this probability, then we are going to simply fire up the LS&D program. And when we are asked for a z-score, then we provide a negative 13.8 for z-score. And so calculation came out that p-value is in 4 decimal places 0.0000. So again, the actual calculation is a lot longer, but even if we already round it down to 4 decimal places, the p-value is still as small as just a 0 in 4 decimal places. And that's the reason why I'm using a 0 point with 4 tailing zeros right here. But this p-value is how big that area shaded in black to the left of our sample mean value on this bell curve. So now we are on the bell curve that represents the distribution of all sample mean values at size 74 in each sample. And so this bell curve is like any other bell curve here, has a big fat area in the middle, right around the center, where we refer to that as the common area. And again, remind yourself that we have proven earlier that this bell curve has center at 80, due to the fact that our null hypothesis h sub 0 was stating that mu equals 80, and for now we have accepted that h sub 0 was true, and we're trying to find out what happened if h sub 0 was true. And so for now, once we have accepted that h sub 0 was true, then that value being claimed in the null hypothesis is the center on our bell curve here, representing all sample mean values. And so the common area is always that big fat area right around that center. And so now again, back on the wording of our problem on the computer screen here, then this problem gives us a significance level being 0.001. So the wording here says at significance level 0.001. Symbolically, alpha is equal to 0.001. That's the symbol for the significance level. But that means, according to what I have explained in the earlier video about with example 1 part A, then the significance level is how big this red area to the right hand side of the common area, and also how big that red area to the left hand side of the common area. So this is our significance level being 0.001 here, and the other red area to the left of the common area being 0.001. Or thinking in terms of thinking as a percentage, then this significance level is being as large as a 0.1%, and here is also it's another 0.1% out here. And so now in that way, now once we understand that each of our little tail here outside of the common area is only as small as 0.1% and 0.1% here, then the math can quickly lead us to finding out that common area in the middle, that big fat area here in the middle, must be as big as 99.8%. All right, and so now, once we have had our common area found out to be 99.8, let's again look at our sample mean value. The sample mean we use here is being 73.65. So at the moment here, clearly our sample mean is below or stays somewhere to the left hand side of this center on our bell curve, which came from the value claimed in our null hypothesis. But now what we want to do now is that we are actually further interested in finding out whether this sample can possibly fall into that unlikely area being outside of this common area. So that's what my arrow is indicating. We already knew that our sample mean is currently somewhere to the left hand side of this center being 80. But we're further interested in finding out whether this sample would fall right into that red tail area on the left of our common area. I will explain the reason why we're particularly interested in finding out whether our sample would further fall into the unlikely area outside of the common area. But for now, right here in this problem, because we're interested in finding out whether our sample would fall into that area, that red area on the left tail of the common area. That is the reason why this kind of testing hypothesis problem, this kind of problem testing a hypothesis, is being referred to as the left tail test. So now what it is being a left tail test is that once we already knew that our sample is lower, is less than or being somewhere on the left of the center on our bell curve, then we're further interested in finding out whether our sample would fall into that further the red unlikely area outside to the left of the common area, and that's what a left tail test is. And now, after I have explained what a left tail test is in this problem right here, then looking back at our hypothesis, h sub 0 saying mu, or stating or claiming that mu equals 80, and h sub 1 is stating that mu should be less than 80. Then usually right at the step where we have identified our two hypotheses, then looking right at the alternative hypothesis here, since the inequality is less than the value being claimed in our null hypothesis, that is already a good sign to indicate that our testing hypothesis problem later on would become a left tail test. And this is the reason why back in the steps when I was showing earlier in this video, then right at the steps where we saw that the H1, the alternative hypothesis, was stating with an inequality being less than the value claimed in the null hypothesis, then I already decided that this test must be a left tail test. But just now I have explained the real understanding of what a left tail test is. And so now, with a different picture of our bell curve that represents the distribution of all sample mean values, the center is at 80, according to the claim in our null hypothesis. And now about our sample. The p-value of our sample was calculated to be 0.0000. And recall that the p-value calculation was set up as the probability that among all sample mean values at size 74, we find the chance that our sample means at size 74 would fall less than or equal 73.65. And so that means, graphically speaking, this probability setup is the same as on the bell curve here. This is where our sample mean value is. It could be there 73.65 somewhere to the left hand side of 80, but this probability problem is graphically represented as the area, and now I'm using black ink right here. The p-value here is, in other words, is graphically the area, the black area shaded to the left of our sample mean value. But then, in that understanding, so now among the steps, we came to a step where there's a direct comparison between our p-value and our significance level, being 0.001 in red ink right here. Simply as a direct comparison, our final p-value came out from this calculation was well below the significance level given in our problem. So that means, or graphically speaking, if we're now about to shade and recall again that this 0.001 is the amount of unlikely area outside of our common area and to the left of the common area. And so according to this direct comparison right now, and here I already put down some drawing, some sketch for my shaded area to the left of the sample value, and this is our p-value here. But p-value in black is supposedly, according to this comparison, less than the red unlikely area outside of the common area. So imagine now that if we would put the two areas together, if I'm now about to put my red area, my red unlikely area, blended together with the p-value on the bell curve, then the picture now is showing that the black area, in the way how it is, being smaller than the red area, then the black area must be completely contain, I'm using that term contain, so the black area being the area shaded to the left hand side of our sample must be in a way that it is completely contained inside of the red area, and the red area here represents how big the unlikely area is outside of our common area. So recall again that our common area in the problem is now here, right around the center. And that common area was calculated previously to be as large as 99.8%. And our significance level here is indicating that this red left tail area is only as small as 0.001. But now our p-value is further showing that the black shaded area, shaded from where our sample is, completed to the left hand side, is completely contained inside of the red area. And so now, looking at that picture, then clearly speaking, it shows that our sample mean value is now clearly among the unlikely values. Because that's the way it is. Look, have a closer look. If you're still not sure, pause the video and have a closer look at the way how I'm blending the two pictures together. The red area is still this big, but the p-value is supposedly the area that's shaded from where our sample is to the left, and that's black area as a p-value is being completely contained inside of the red area. Then that means x bar itself, the sample point itself, has to be somewhere inside of the red area. And now I can say in my final words, x bar, our sample mean value, is among the unlikely values, because the red area represents the area where it contains all the unlikely values. And then that leads to a stronger statement saying that now our x bar, our sample mean itself, is an unlikely value itself, because it's being among the unlikely values. And so now we can further say that the sample value we've had, 73.65, is an unlikely value itself. And now, as I have explained quite a few times back in the earlier video when I was going over part A of our example 1, then the common area on any bell curve represents the area where we have sample values that can be commonly fluctuating away from our center, which came out from the claim. And so directly applied into our situation here, yes, once again, our center is being 80, and it came out from the claim, from our null hypothesis. And so our common area is being as large as 99.8%. That means any sample mean values is expected, of course, to be differ from this value. Some sample can be above, some sample can be below, because in the end, anyone making a claim is a human being. No one can only at one shot claim a precise value. And so we must accept a certain amount, we must tolerate a certain amount of fluctuation error. What matters now is our sample, even though fluctuated away from the claim in the center here, but is it a commonly seen fluctuated sample value, or a sample value that falls into the unlikely area, indicating it is an unlikely sample value that fluctuated away from the center being claimed. And so in that case here, with the common area being as large as 99.8, our sample being 73.65, and any other one, and any other x bar right here is expected at 99.8% probability or chance to be in the common area. What this means is that anytime we picked up, if our null hypothesis was true, if the null hypothesis stating that mean pulse rate is equal 80 beats per minute, if that was accepted and truthfully correct, then anytime we're picking up a sample, our sample here or any other sample mean value is expected to be, even if fluctuated away from the center here, but it is expected at 99.8, such a high chance at 99.8 probability to be in a common area. That means it's just one of those values that we can commonly expect to differ from our claim here. And another way of saying is that the sample we picked has only a 0.01 chance being out in this red area. The chance being in this red area is only a 0.001 chance. Or if we find any other sample, then other sample may be higher than this claim, but only has a chance being 0.001 chance to be above that to be in this unlikely area to the right hand side of the common area. So we shouldn't expect our sample to be in anywhere outside of the common area, because the common area already accepted such a high chance. But no, our sample value, sample mean value 73.65. One sample, any sample is selected at random and supposedly easy to select. 74 people in a sample is not so big for a sample, but that we have already proven that this sample is immediately, and immediately what I mean is the only sample we found has already been proven to be inside of that unlikely area. So I'm saying now that x bar being 73.65 is immediately in the unlikely area. Something that we shouldn't expect our sample mean to fall in there, but it's now in there. The only one sample and supposedly easy to find, but it's already fell right into the area where things are supposedly not happening that often at all. And so that's the reason why our sample, now we can make a conclusion that our sample mean value is a strong evidence, or showing strong evidence, or itself is a strong evidence. And this strong evidence is for the purpose to, either we can say we have to reject h sub 0, or we can say to, we have strong evidence, our sample is strong evidence for us to support the alternative hypothesis, saying that it is suggested that mu should be less than 80, because hey, 80 is a little too high so that even if we already accepted 99.8% of sample mean values to be values that are commonly fluctuated away from this claim, but our sample still stands right into that area where we should expect at a 0.001 chance to be having a sample value in there. And that's the reason why it is a strong evidence to either reject h sub 0 or to lean toward that or to support that hypothesis h1. All right, so before we are completely finished and move away from this part B of our example 1 right here, then let me make a further clarification on the notion of the alternative hypothesis. So we already knew that our null hypothesis was that statement claiming that mu equal 80. Mu equals 80. It is this is the mean pulse rate. The population mean pulse rate equals 80. So we've learned throughout testing hypothesis problem that once if we accepted this claim, then on that sampling distribution bell curve representing all sample mean values at size 74, then this claim value would be placed right at the center of the bell curve. But then further, together with the fact that we had a common area being as large as 99.8%, then our sample being 73.65 fell outside of the common area and fell right into that unlikely red area to the left of the common area. And that's how this sample made it a strong evidence to reject the claim to be at 80. So now think about if that person who made this claim or anyone else who saw this claim and rejected that claim can make a different claim by suggesting a value for mu that is generally below 80. Now, so here be careful that I'm not specifically pointing to any particular value, but I'm saying that generally if we can bring this, because right now being mu equals 80 is being too high, our sample appear too low so that it already fell into the unlikely area. So now we can suggest a different value being lower than what we have already claimed previously. And so in that case, let me draw another bell curve and describe that other scenario. So now, if the person who initially made this claim or anyone rejected this claim has made another suggestion that this mu should be less than 80, then think about we can think about a different value for mu that is less than 80. Then if that other claim, if that new claim being somewhere less than 80 is made, once that's claimed, then consequently again it will become the center on the sampling distribution bell curve. Notice that this is still the distribution for capital X bar 74, but the center now is being brought to a different place simply because we have brought our claim to a different value, and more specifically this value is lower than 80. And so in that way, think about the consequence. If we brought our claim value to a value somewhere lower than 80, then anywhere we bringing our center to, the common area being as large as 99.8% will also be shifted along the way. So think about if we can bring our claim value to somewhere lower than 80 and lower enough so that eventually this common area will contain our sample mean inside of that. Or another way of seeing that is that if we can possibly bring our claim value down to a place where the sample mean would now belong to the common area 99.8% around that new claim value, then at that point, once the sample would become part of one of the common values inside of the common area around the new claim here, then there we're going to say the sample is not a strong evidence, or is not showing strong evidence. Simply because X bar is among the common value, the common values, if we brought that claim further down far enough, that x bar would eventually fall inside of the common area. And there x bar is among the common values, which means those are the values that commonly fluctuated away from the center, even though we already brought it to a different center. And so in that case, x bar would be accepted, and accepted as a value that can possibly be fluctuated away from the center. And so in that case, nothing is wrong with our sample if that case happens. And so that's another way of seeing about coming up with an alternative, suggesting a value that is generally lower than 80, because once we are suggesting a new value, then the new value would become a new claim lower than the one originally claimed. Then after that claim is being brought to a lower value and lower enough so that our sample would fall inside and become a common value, then that's where we will fail to reject. Another note here is that we will fail to reject H sub 0. And of course, I have to add a note that if we put a new claim, then that means the new claim is a new null hypothesis H sub 0. And so that is the whole idea about coming up with an alternative hypothesis. We're suggesting a new claim, a new value, definitely lower than 8, lower than what's originally claimed here in the null hypothesis, and lower enough so that the common area around it would contain the sample that we already had. And once the sample falls among the common values, then nothing's wrong with that sample. It's among the sample that we can accept as some fluctuations. And so there it's not strong evidence to, and we fail to reject the new claim, the new null hypothesis.